A 4 kilogram block is attached to a spring with a spring constant of 200 newtons per meters, which is attached to a wall. The block is at rest, the entire frictionless surface. The block is pushed 5 centimeters to the right, causing the spring to compress and released at t equals 0. First thing we want to do in part A is calculate the frequency of the resulting oscillation. We know the formula for the period of a mass spring system is T is equal to 2 pi times the square root of m over k, and the frequency is just the inverse, or the reciprocal of this, 1 over 2 pi times the square root of k over m. So if we plug in 1 over 2 pi times the square root of the spring constant, which is 200, divided by the mass of 4, 200 divided by 4 is 50, and 50, since it's under a square root sign, can be broken down into 25 times 2, since 25 is a perfect square. So this becomes 5 root 2 over 2 pi hertz. And if you plug this into your calculator and solve that, you will get the answer printed on the sheet of 1.125 hertz, but I'm going to leave it in this form right now, and you'll see why for part B. So in part B, write an equation to express the displacement of the block as a function of time t. The general equation for simple harmonic motion is x equals a times the cosine of 2 pi f t, and we were going to write x as a function of t. So we need to plug in something for the a, and we need to plug in something for the f, so we're just left with x as a function of t. The a is the amplitude, and it said in the problem the block is pushed 5 centimeters to the left. So the a is going to be 5 centimeters. So we can write this as x is equal to 5. Now, if you wanted to express x in meters, then it would just be 0.05, but I'm just going to leave x expressed in centimeters for this one. So we'll leave it as 5 times the cosine of 2 pi. Now let's take what we just got for the f up here and plug it in down here. That's going to be 5 square root of 2 over 2 pi, and then close it off with the t and close the parentheses. And now you see why I left it in the exact form, because we have a 2 pi in the numerator, which cancels with a 2 pi in the denominator. So we can just write our final answer as the x equals 5 cosine of 5 root 2 times t. For part C, want to calculate the maximum acceleration the block can achieve. We know it reaches its maximum acceleration at the endpoints, because at the endpoints, that's where the x is stretched, that's where the spring is stretched the most. So the x is equal to, and this time I'm going to go ahead and write it in meters, so it's 0.05 meters. And then from there, I can get the spring force, which is just the k times the x, and the k was 200. So we have 200 times 0.05, which is going to give you, that's going to give you 10 newtons per meter. And then the acceleration at that endpoint is just going to be that spring force divided by the mass from Newton's second law. So that'll just give you 10 divided by 4, and you get an acceleration of 2.5 meters per second squared. For part D, how much time after t equals 0 does it take the block to reach its maximum acceleration in the first cycle? Since the block was pushed to one side and released, it was released at an endpoint, which is where it already has a maximum acceleration. But this is saying how much time after that point does it take to reach the next time it reaches its maximum acceleration, which would be at the other endpoint. If the block oscillates from one side to the other side, and then back to where it started, it has a maximum acceleration at this endpoint where it's released, and a maximum acceleration at the other endpoint, which is going to be half of the total period. So let's figure out the period, which you can get by doing t is equal to 1 over f. Use the f you got from above to get the period, and then just take half of that. So the t divided by 2 should give you your answer. For part E, part E, calculate the maximum speed the block can achieve. The maximum speed is the thing you find by setting conservation of energy, because you're going to be turning the elastic energy from the endpoints into the kinetic energy of the block. So let's just kind of shortcut this and say 1/2 Ka squared, which is the elastic energy at the endpoints, or the maximum elastic energy, is equal to 1/2 mv squared. That's the kinetic energy at the midpoint, or the maximum kinetic energy. And I'll put a little max on here to indicate that's the velocity at the middle. The 1/2s on both sides cancel out, and you can just solve this to get Vmax by itself. So just divide both sides by the m and take the square root. So Vmax is equal to k, the square root of k, which is the 200 times the a squared, and the a was 0.05 squared if we're putting everything in standard units, divided by the mass of 4, and when you plug all that in, you should get the maximum speed of 0.35 meters per second. In F, it wants to know how much time after it's released will it take until it achieves the maximum speed. We know the maximum speed occurs right at the center, the equilibrium point. So if I go back up to this diagram right here and draw this blue X at the center point, that's where it gets its maximum speed, and that's half of this, or 1/4 of the period. So just go back to the period that you found, and instead of taking half the period like you did in part D, just take 1/4 of the period, and you should get that answer of 0.222 seconds. And then finally in part G, it wants you to graph x versus t for one full period. So x is the displacement from equilibrium. We were told it was pushed 5 centimeters to the left. So we haven't really defined positive and negative. So let's just define to the left is negative and to the right is positive, which means when the block is released, it's at its negative amplitude. So the amplitude is the 5 centimeters. So I'll leave this graph expressed in centimeters versus seconds. So if this is going to be negative 5 centimeters, then the graph's going to fluctuate between negative 5 and positive 5 centimeters. And it's going to start, let me put the other points on the graph. So we have, that's the halfway point of the period, that's the 1/4 point, and the 3/4 point. We know the graph is going to start at negative 5. After one full cycle, it's going to end at negative 5. And then in between then, it's going to oscillate through that point to the maximum on the other side at the halfway point, and then back down to, and that should cross right at that point, back down to negative 5. So it reaches positive 5 at the, which is the other endpoint, at the halfway point on the period. And the other thing to graph is kinetic energy measured in joules versus time, and that's also for one period. Now, one thing if you remember about kinetic energy is that kinetic energy can never be negative. So on your graph, you should not have anything down the bottom here. You should only have positive values for the kinetic energy. When the block is first released from its endpoint, it is not moving. it's released from rest, so the initial kinetic energy is 0, which means when it gets back to that endpoint, the final kinetic energy will also be 0. And when it reaches the other endpoint on the other side, right here, the kinetic energy is also going to be 0. So it becomes 0 at 3 points, and you reach maximum kinetic energy when it's passing through its equilibrium point, which is right here and right here. So I should have a dot at the maximum at that 1/4 of the period, and then again at 3/4 of the period. And then we can connect these points, and it forms kind of like an absolute value looking thing of a sine curve. So it looks like 2 bumps, because if kinetic energy could be negative, the graph would go down the bottom here, but we're kind of taking the absolute value of that second part of the graph.